Hello, everyone. My name is Archis Gate, and I'm a professor at the University of Washington in Seattle. This tutorial is about response-guided dosing in cancer radiotherapy. Let us get started with some background on cancer. The World Cancer Report states that millions of people around the world will continue to suffer from cancer in the near future. Cancer is also a major cause of death in the US. There is 3 ways to treat cancer: surgery, chemotherapy, and radiotherapy. This tutorial is going to focus on radiotherapy. Radiotherapy is administered in one form or another to about half of all US cancer patients. And the tutorial in particular focuses on external beam radiotherapy. So let us look at some background on external beam radiotherapy. This image taken from the National Cancer Institute website shows that the patient is here on the couch and radiation is delivered from this machine. Okay. Radiation emerges from this part of the machine and passes through the patient's body. The goal is to kill the tumor in the patient's body using that radiation. Now, the challenge here is that radiation damages not only the tumor or the cancerous region, but also the healthy tissue, or let's call it normal tissue, that is nearby. So the goal in external beam radiotherapy for cancer is to maximize tumor kill subject to toxicity limits on normal tissue. So that means that you want to limit the toxic effects of radiation on healthy tissue that are near the cancerous region. And this is pursued by using a three-pronged approach. The first component of that approach is spatial localization of dose, which basically means that a high radiation dose is prescribed to the tumor and a low dose is given to the normal tissue. Dose here means radiation energy per unit mass, by the way. The second approach is temporal dispersion of dose. This is also called fractionation in the clinical literature. And the idea there is to distribute the dose over multiple treatment sessions. And this is motivated by the fact that healthy cells have a better capability to recover from damage as compared to tumor cells. And distributing dose over time actually gives the healthy cells some time to recover between sessions. And the third approach is modality selection. So radiation can be delivered using different modalities such as photons, protons, carbon ions, and so on. But each of these modalities comes with distinct biological and physical properties, and we'll talk a little bit more about that later. But because of those distinct biological and physical properties, the idea here is to which modality should be used for a particular patient or for a particular cancer type, or should a combination of the modalities should actually be used. Okay, so these are the 3 sort of approaches that are used in order to meet this goal, the goal of maximizing tumor kill subject to toxicity limits on normal tissue. So let's get into a little bit more details behind this, or about this spatial localization. This picture shows the main idea in spatial localization. You can see that the schematic shows a tumor that is this boomerang-shaped region over here. And OAR is just another name for normal tissue. OAR means or stands for organ at risk. Okay, so what is shown in this picture is that the radiation intensity profile is actually modulated in a certain way. So the intensity is higher going that way. And the way it is done is that we want to give low dose to this OAR or normal tissue. And that is the reason why a low intensity radiation profile is used in that area. Okay, whereas higher intensity is actually used in this part and this part, so that you can actually damage the tumor cells or kill the tumor cells in this region versus this and this region. You can see one problem with this picture, and that is that because I'm using a low intensity profile in the schematic over here, this part of the tumor is going to get, let us say, insufficient dose. Okay. And to compensate for that, this is called a cold spot in the tumor. And to compensate for such cold spots or to avoid such cold spots, radiation is actually delivered from different angles. And this schematic actually shows that idea. So you can see that in this part, right, high intensity use is used so that this part of the tumor is killed. This side also high intensity is used so that this part of the tumor is killed, but a low intensity profile is actually used in this part in order to protect this organ at risk, which will mean that there will be a cold spot here in the tumor. And to avoid that cold spot, this different direction is used. Okay. And in particular, you can see that this high intensity radiation will actually reach this part of the tumor and perhaps avoid or at least reduce that cold spot issue that I mentioned. Similarly, this will actually do the same job. Okay, so this is the reason why multiple directions are actually used in the spatial localization, on the spatial localization side. I want to go back for a second and show you that machine that I had shown you in the picture here. So this machine actually can rotate. Okay, and this is how the machine will rotate, and then that's how different sort of directions are used to deliver that radiation for spatial localization. So let us remember that for a minute and then move on to the idea of temporal dispersion. I had briefly mentioned that the idea there is to give the healthy cells, normal tissue, right, some time to recover between sessions. And this schematic sort of tries to convey that idea in a simple way. So the schematic actually shows on the x-axis, there is dose. So again, radiation energy per unit mass. And on the y-axis, there is damage to the normal tissue, and the damage is more going this way. Okay, so that's the idea. And this basically shows how much damage will be done to the normal tissue if dose D1, as shown here, is given in one treatment session. And this dotted line shows that the damage, suppose, is this much. Okay, so this is just a schematic curve showing that damage done. Okay. However, the important part of the picture is that it turns out that if I actually broke that dose D1 into 3 sessions, as shown by the curves AF, FG, and GH, it turns out that the damage done to the normal tissue is actually less. As you can see from this picture, the damage will only be this much. Okay. And this is what we mean by saying that, okay, by breaking the dose down or by doing temporal dispersion of dose, we'll be able to reduce damage done to the normal tissue for the same amount of total dose D1 in this particular case. Okay. Now, what I'm not showing in this picture is that the tumor, let us say, is also going to have a similar sort of curve, right, characterizing its behavior. And also the tumor is actually going to grow, right, so proliferate over the treatment course. So the main idea in temporal dispersion is how to trade off between these different ways in which the tumor, let's say, and different normal tissues actually react to radiation. And in particular, how do we use that to maximize tumor kill without harming the normal tissue too much, right? So by limiting the toxic effects of radiation on the normal tissue. So that's the idea in temporal dispersion. And I mentioned the third approach has to do with modality selection. So again, this schematic actually shows the idea behind sort of different modalities and how they behave. In particular, this is basically showing what is called the dose deposition profile schematically of 2 different modalities, photons and protons. On the x-axis, I have depth in the tissue and the relative dose that is actually delivered or administered at that particular depth in the tissue. So you can see that the photon profile is actually much different from the proton profile. And in particular, the photon dose deposited increases to this peak and then reduces in particular actually exponentially after that. Whereas for protons, it gradually increases, right, slowly, then has a very sharp increase, reaches this peak, and then has a very sharp drop. Okay, this peak is called Bragg's peak. Okay, and as you can see, it is quite different from the way the photons actually deliver dose inside the normal tissue or any tissue for that matter. Okay, so the idea, because of this difference, is which modality will be actually the best for a particular cancer type, for example, right? Or should we use a combination of these 2 modalities? So that has to do with that is at the heart of this modality selection question. So what I'm going to do in this tutorial is I'm going to look at spatial localization, temporal dispersion, and modality selection within the context of the so-called linear-quadratic or LQ dose response framework. According to this framework, the surviving fraction of tumor cells is given by this formula. This formula has several pieces, so I'm going to walk you through each one of those. The number of sessions here is capital N, indexed by t equal to 1 through n. The dose given to the tumor in the tth session is dt. So this formula has this term that is the sum of doses. So this is the linear term in the linear-quadratic dose response framework. And you also have a similar squared term, dt squared, also added together. So this is the quadratic term in the LQ dose response framework. Tau n here is the so-called proliferation term. Remember, I mentioned earlier that the tumor actually grows during the treatment course. And the typical formula, the sort of commonly used formula for this tau of n is tau n equal to this form. Here in this form, T double is the doubling time. This is the amount of time it takes for the tumor cells to double, let's say number. And n minus 1 is simply the number of sessions n minus 1. The assumption here is that one session is actually delivered each day. So when you actually have n sessions, the tumor cells get n minus 1 days to grow. And that's the reason why this term actually shows up here. Okay. So this is again exponential negative alpha 0. Alpha 0 is a parameter of this framework. Beta 0 is another parameter of this framework. Okay. So exponential negative alpha 0, sum of doses, negative beta 0, sum of square of doses, plus a proliferation term. So this is the surviving fraction of tumor cells. Now this is the most widely used dose response model in the radiobiology literature. And the tutorial is therefore going to focus on this model in all the remaining slides. And in particular, the tutorial is going to look at optimization methods for spatial localization, temporal dispersion, and modality selection to guide decisions based on this particular dose response framework. And this is the reason I titled the tutorial as response guided dosing, okay, in cancer radiotherapy. And what I'm going to do is I'm going to present the tutorial through the lens of the so-called optimal fractionation problem. So I've not yet mentioned what that problem looks like, but that problem actually nicely sort of incorporates the spatial component, like I mentioned earlier, the temporal component, as well as the modality selection component into it. So that's the reason why we are going to look at this through the lens of that optimal fractionation problem. And in the tutorial, I am actually only going to look at exact solution methods, meaning methods that will give us an exact answer to whatever optimization problem we are going to formulate. Okay, so let us get started. As I mentioned, I'm going to look at everything through the lens of the optimal fractionation problem. So let's first look at optimal fractionation with a single modality. So I mentioned the modality selection idea earlier, and I will talk about two modalities later on, but let's begin with the simpler case of single modality. So the optimal fractionation problem within the LQ dose response framework with a single modality is usually formulated in this form. So let's look at what the problem is. I'm going to call this problem opt-frac for optimal fractionation. The decision variables in this problem are n, which is the number of treatment sessions n, and they're between 1 and some maximum, right, possible number of treatment sessions. So it's between 1 and n max. It's an integer. And the dosing vector. And I mentioned earlier to you that d subscript t is the dose given to the tumor in the tth treatment session. So d1, d2, dot, 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 up to dn is my dosing vector. And of course, that vector is a non-negative vector. So I want to figure out that non-negative dosing vector and the number of sessions that I'm going to use for the treatment. In the numerator, in the objective function, you will see that I am maximizing this quantity. And I think you'll recognize that this quantity that is showing up in the objective function is precisely the negative of what I had in this surviving fraction of tumor cells formula, the negative of what I had here, that's what is showing up. And the reason for that is that this is the surviving fraction of tumor cells. So I want to minimize this exponential, the whole thing, which means I want to minimize whatever is inside, which means I want to maximize the negative of that. So that's the idea. And that is being actually maximized in the objective function of that problem. So that's what you will see here. Okay. And again, as I said before, alpha 0 and beta 0 are parameters of this linear quadratic dose response framework for the tumor. Now let's look at these constraints in some more detail. M here, capital script M here, is the set of normal tissue. So for example, in head and neck cancer, you might be looking at different normal tissues that are near the tumor, such as, let's say, spinal cord or brainstem, or your saliva glands and things like that. So that set of normal tissue is denoted here by script capital M. And of course, elements are indexed with this little m over here. In other words, there is a constraint like this, okay, for each normal tissue, okay, in this problem. And let's look at what the constraint is doing. The constraint, in some simple fundamental way, the constraint is trying to put an upper bound on the toxic effect of that dosing plan. Okay, so on the left-hand side, in other words, what we see is the toxic effect, okay, of that dosing plan on that particular normal tissue. Now let's break this down a little bit more and look at it a little bit carefully. SM here is called the so-called sparing factor. Okay, SM is the sparing factor. And the idea there is that if dose DT is administered to the tumor in the T treatment session, then a scaled version of that dose, in particular SM times DT, will actually be delivered to the mth normal tissue. And this sort of captures the spatial localization component of the problem. As I mentioned to you earlier in those pictures, for that spatial localization idea, right, we'll actually have an intensity profile which will determine what dose is given to the tumor as well as what dose is given to each particular normal tissue. And that sparing factor can be calculated based on that geometry or anatomy of the problem, okay, the physics of the problem. So this is the sparing factor. You see this as a squared term here because we have dose squared here. So corresponding to that, you have an SM squared here. Rho m is a parameter of this linear quadratic dose response framework for this normal tissue. So that's what is showing up here. This rho m is actually equal to 1 over alpha over beta for that particular normal tissue, where just like the tumor has this alpha 0 and beta 0 parameters, each normal tissue is also going to have an alpha m, let us say, and a beta m parameter that goes with this LQ dose response framework. And this rho m is actually 1 over that alpha m over beta m ratio. Okay, so that's what is showing up here. And in the radiobiology literature, what is being seen on the left-hand side here is called the biologically effective dose. Or in other words, this is sort of, we can think of this as the biological effect of that particular dosing plan on that normal tissue. Okay, and the idea here is to keep that effect, biological effect, below a certain tolerable limit. Now let's look at what this tolerable limit is and what the parameters of the numbers are here. Okay, so TM is the number of treatment sessions in a conventional treatment plan. So for example, for head and neck cancer, the conventional treatment plan might be 35 treatment sessions. So that number 35 is going to go in here. And in particular, let's say that the normal tissue that I'm looking at, let us say spinal cord or something like that, suppose it is known to tolerate a certain amount of dose that is being called delta M here per session in these many sessions. Okay, so that's what you're actually seeing here. And rho m is, of course, that parameter of that normal tissue that I was talking about earlier. Okay, and again, delta m is showing up here. So if you actually expand this out, this is again going to be Tm delta m plus Tm delta m squared rho m. So it has basically the exact same form that I have here. And in particular, on the right-hand side, what I have is the biologically effective dose corresponding to that conventional treatment plan that that particular normal tissue is actually known to tolerate. Okay, And I'm calling that CM for brevity here, but that's the upper bound. So what you want to do is you want to figure out a treatment plan, but you do not want its toxic effect on that normal tissue to be more than what the normal tissue is actually known to tolerate. Okay, so that's sort of the main points of this model, and the objective function, the maximum value, I'm calling that as F star. Okay, so this is called the optimal fractionation problem. One sort of natural way to look at this problem is to actually fix n first. Okay, so fix n, and then whatever the problem is, when we fix n, let's call that opt-frac n, right, to denote that n is fixed. And you solve that problem opt-frac n. Okay, and after solving that problem, you get an objective function value for that particular problem with that fixed n. And you can do the same for every integer n between 1 and n max. And then you'll have all those n max different objective function values, and you simply pick the best. And that would be one way to actually approach this problem. And that's why it's common to simply focus on this problem for a fixed n first. And that's what I'm going to do for now. Okay. It turns out that if you actually look at this problem, so let's look at the form of this problem when n is fixed, right, for the moment. So when n is fixed, okay, this is just a constant, essentially tau of n. N is fixed, right? The sum is equal to 1 to n, linear terms, quadratic terms. If you look at this expression, linear quadratic expression in the objective, it is actually convex, but it is being maximized. Okay, it is being maximized. The convex function is being maximized. And that's what actually makes this problem non-convex. Okay, if you look at the left-hand side here, right, that is actually again linear quadratic convex. Okay, so the feasible region of that problem with n fixed is actually a convex feasible region. Okay, in particular, this is a quadratically constrained quadratic program, okay, called QCQP for short. But it is a non-convex QCQP because the objective function is actually convex, but it is being maximized when n is fixed. Okay. So what we're going to do is we are actually going to look at this problem closely, and despite the fact that it is a non-convex problem, we'll be able to show that we can actually solve this problem exactly, okay, using a very simple technique. And the way we are going to do that is we are going to actually exploit this observation that this problem, opt-frac n with n fixed, of course, is actually equivalent to a two-variable problem. And here is the two-variable problem. Okay, so again, I'm fixing n, so I'm writing that as f star of n. Okay, this is the objective function. And see what I did here? I actually replaced or substituted x for the sum of doses and y for the sum of square of doses. So that's what I did. And that's why I got this form for my objective. And again, I noticed that the same form, sum of doses, shows up here. So I put x in place of that. And I noticed that sum of square of doses shows up here. So put y for that, less than equal to cm. So I was able to write the objective as a linear objective in x and y, linear in x and y, and also the constraint as linear in x and y. And x and y are actually going to be non-negative here, right? Because the doses are non-negative. So the x is non-negative and y is of course sum of squares. So that is non-negative. So I put those constraints here as well. But this constraint is actually an important one. And I want to talk about that for a minute. Okay. So when I actually did this change of variable, I cannot ignore the fact that x and y are actually related to one another because x is sum of doses and y is sum of squares of doses. And if you think about it for a minute, that basically means that x is, doses are non-negative. So x is the L1 norm, right? And y is the square of the L2 norm. So when that is basically the case, the x and y are related by these inequalities, okay? This is a standard inequality that basically relates L1 and L2 norms. So square root of y less than equal to x less than equal to square root of ny. And I cannot actually ignore this constraint because x and y are actually related in that manner that I just described. Okay, so I inserted this extra sort of two inequalities, if you will, in addition to the objective function and the constraints, right, that now have x and y. So these two problems are actually equivalent, okay, meaning that I could actually solve this problem The good thing about this problem is that it only has two variables. Okay, the problem is still actually not convex. Okay, because one of these two inequalities is actually non-convex constraint. So the problem is still not convex, and I'll talk about that in a minute. But at least it's a two-variable problem. And I'll talk a little bit about what I mean by equivalent here on the next slide. So let's go to the next slide. And what I mean by equivalent is really driven by this constraint, okay? This constraint that I just explained, the new constraint that was introduced. And in particular, if I solve this problem and I obtain X star and Y star as a solution to this problem, I can always use that X star and Y star to actually recover a solution to this problem, okay? That's what we mean by equivalent here. And you can read up a little bit more detail behind that in the tutorial paper, if you will. But roughly speaking, what that means is that if I have X star and Y star, it turns out that there is only three possibilities. Okay, Y star could be equal to X star, and square root of Y star could be equal to X star, and that's when this is equal to this. Okay, that's one possibility. The other possibility is that X could be equal to square root of ny star, when this is met as equality. Right? And the third possibility is that X star is strictly in between these two quantities. So these are the only three possibilities. And it turns out that for each one of those three possibilities, I can use that X star and Y star to recover a dosing plan D1 through Dn. So let us see how we can do that. The first case is where square root Y star is equal to X star. And it turns out that the only way that can happen is if exactly one of the doses is X star and all the other doses are 0. And this is what I'm illustrating here, that let's say, for example, I'm setting D1 to X star and all the other doses to 0. The second case is where X star is equal to square root ny star. And the only way that can happen is if all the doses are actually equal. And since the doses have to sum up to X star, each one of them should be X star divided by n. The third case is a little bit more complicated, and that is where X star is in between these two quantities. But when we say in between, the question is where in between, and therefore there is various different cases for different values of integer k between 2 and n. X star is between k minus 1 y star square root and k y star square root. If that is the case, we can actually recover the first k minus 1 doses using this formula, the kth dose using this formula, and the doses k plus 1 and beyond are 0. So this is one possible way in which this situation can actually arise. So this is the reason why, going back to the previous slide, these two problems are actually equivalent. So instead of focusing on this problem with n fixed, we can just look at this problem, of course, with n fixed. So let us keep that in mind and try to get further insight into these problems. So what I'm going to do now is I'm going to actually derive a closed form solution to the problem that we were looking at when there is a single normal tissue. Okay, and the reason I'm doing that first is because that does provide some intuition and insight behind what is going on. And then we will actually generalize to the case where we can still solve exactly the multiple normal tissue case. So just to emphasize the fact that we only have one normal tissue now, I'm going to sort of put this one, as a label in front of my problem names. So upfrac 1 with n fixed is going to look like this. You won't see any difference in the objective. The only thing I did was that I only have one OAR now, or one normal tissue now. So I dropped normal tissue subscript m and simply wrote this as my one single constraint on that particular normal tissue. And of course, using the same idea as I was describing earlier, this problem is equivalent to this problem. So I replaced the sum of doses with an x and the sum of square of doses with y. I did include this particular constraint, and that's what gave me this problem. So when one normal tissue is there, okay, only this one constraint for that normal tissue. And then I'm going to actually show a picture that describes the situation in this two variable problem. The variables are x and y. So this is a linear objective, this is a linear constraint, but I have these two constraints that I have to pay attention to, and x and y are non-negative. And that is shown in this picture as this gray feasible region, shaded gray feasible region. So x-axis, y-axis, this is the origin. And this is that one of those two inequality constraints that I've been talking about. This is actually the boundary of that constraint where x is equal to square root ny. And on this curve here, that's the boundary of that inequality, the other inequality where x is equal to square root y. Okay, so that's the feasible region here, curved feasible region, horn shaped. And then of course there is a linear constraint, and I am showing that here with this, right? So I'm calling that normal tissue constraint. Remember, BED stands for biologically equivalent dose, right? So that's a normal tissue constraint that I have. And if you looked at the constraint, the way it looks going back, this is the form of that constraint, right? That this BED has to be less than equal to some tolerable limit. And the slope of this constraint can actually be easily calculated. Its magnitude is actually alpha over beta 1 over S. And remember that alpha and beta here are parameters of that linear quadratic dose response model for that normal tissue that I'm looking at. And in particular, the rho that shows up here, as I mentioned earlier, is equal to 1 over alpha over beta. Okay, so anyway, that is the slope magnitude. So this is the problem that we want to solve now. And remember that the objective function now, by the way, this tau n is just a constant because n is fixed. So objective function here is simply alpha 0 x plus beta 0 y. By the way, these alphas and zeros, alphas and betas are basically positive parameters, positive constants, right? So the way this is going to work is that I want to draw a linear contour line and I want to push it as much as possible that way, right? Because I'm maximizing basically alpha 0 x plus beta 0 y. So this is that objective function contour line. And I want to push that out that way as much as possible. And it turns out that if you look at this picture, there are two possibilities. So since you want to push that line out as much as possible, optimal solutions to this problem are going to lie on this part of that feasible region, this line segment, if you will. Okay, they're not going to lie over here because I want to push the line out as much as possible that way. So then the question is the solution going to lie here at this corner point or at that corner point? Okay, and you can intuitively see that if the slope of this line is this way, right, then I try to push it as much as possible that in that direction, then the optimal solution is going to occur over here. And what we mean over here is that the slope here is flatter than the slope of this constraint line. Okay. The other situation is where the slope of that objective function contour line, which I'm showing here, is actually steeper, okay, than this constraint line. And in that case, the optimal solution is actually going to lie at this corner point. And this shows to me that if I look at what is the slope of this objective function contour line, it turns out that the slope is actually alpha 0 over beta 0. And you can figure that out just by looking at this objective function. So this tells me that if the slope here, right, is steeper, so if alpha 0 or beta 0 is bigger than this quantity, then the solution is actually going to lie at this corner point. And on the other hand, if this is actually smaller than this quantity, then the solution is going to lie at this corner point. That's the idea. And I want to actually emphasize the importance of this corner point versus that corner point. You can see from this picture that this corner point actually lies on this curve x equal to square root y. And if you go back to my earlier discussion about what that means, being x being equal to square root y, we know that this solution has this property that only one dose is actually x star, all the other doses are 0. And this is what we are going to call a single dosage solution, where there is only one dose that is, some positive number, let's say. All the other doses are actually 0. Versus when x star is square root n y star, all the doses are actually equal. We are going to call this an equal dosage solution. So the importance of that is that if this slope is steeper than that slope, then my optimal solution occurs here, which is an equal dosage solution, okay, because it lies on this x equal to square root n y curve. On the other hand, if this slope is flatter than that, then it occurs here, the optimal solution, and that's going to be a single dosage solution. Okay, and that basically gives us this proposition. So like I said, suppose alpha 0 or beta 0, these are the parameters of the tumor tumor linear quadratic model. If they're bigger than this 1 over S alpha over beta, remember S is the sparing factor for that normal tissue, and alpha and beta are the parameters of the LQ dose response model for that particular normal tissue. Then, as I said, it is optimal in that problem with a single normal tissue, of course. to deliver doses that are all equal to each other in all the treatment sessions. Like I said, it's equal dosage solution. And then the question is, of course, what is that equal dose, right? That equal dose, we know it's going to be x star over n, but going back to the original problem, right, we can actually figure out what that value must be. And it turns out that that value must be this expression, or is given by this formula. And you can see that this formula has a similarity to a typical quadratic equation solution, right? Formula, minus something plus square root of something divided by something else. So this has that form. And the reason that it has that form is that if you go back to the original problem, so I'm going to show you this original problem for the single normal tissue case. This is what the constraint looks like. Now we know that there is only single normal tissue, and the higher the dose, the higher the objective, right? So therefore, this constraint must be active at an optimal solution. And the moment I know that this constraint has to be active, right? And the moment I know that an equal dosage solution is optimal, as shown in that proposition, because the ratio of alpha over beta, right, alpha 0 or beta 0 is bigger than 1 over S alpha over beta for the normal tissue, I know that an equal dosage solution is optimal. Then I can simply set all these doses to be equal to one another. So here I'll get a term which is n times the dose in any one of those sessions. And again, n times the dose squared, right, for any one of those sessions. And this has to be equal to C because the constraint has to be active, which tells me that I can simply solve that quadratic equation in D and figure out what that optimal equal dosage solution must be. And that is how we were able to derive this particular formula, okay? On the other hand, if alpha 0 or beta 0 is less than 1 over S alpha over beta, then it is optimal in that problem to set all the doses to 0 except 1. And what is the optimal value of that dose? Again, you can go back to the same constraint that I was emphasizing a few seconds ago and solve a quadratic equation to find out the value of that dose. And it turns out that this is the value of that dose. And let's see why. Because if you go back, and if you know that, of course, this constraint is active, but a single dosage solution is optimal, meaning all these doses, there is only one of them, all the others are 0. So let's call that D. So you simply get SD, S squared, rho, D squared equal to C. And you can simply solve that quadratic equation. And when you solve that quadratic equation, you'll get this as its solution, as you can quickly imagine, right? So this is that optimal single dosage solution, which occurs in this particular case. And then, you know, when these two are actually equal, then you are essentially indifferent than any dosing plan that satisfies that constraint that I've been talking about, right? Equality constraint is actually optimal to that particular problem. And that is when the situation in this picture is such that the slope of this contour line, the objective function contour line, actually matches the slope of this. So anything that lies on this line segment is actually optimal, okay? And that's in the XY variable space. But translating that to the D variable space simply means that any solution D, D1, D2, Dn that satisfies this constraint, equality constraint, is actually optimal. So this is a solution to that problem with a single normal tissue. You can actually get further insight into that proposition that I showed you by drawing the feasible region for that problem that I was talking about. Let's go back and look at this problem now by drawing the feasible region for this particular problem and looking at, you know, what are the sort of the contours for the objective function in this problem, and what are the sort of what is the shape of this feasible region. It turns out that this is actually an equation of a circle or a disk, if you will, okay? And this is an equation of a circle when I set this to be equal to some particular constant, right? When I'm trying to draw the contours of this objective function or level sets of this objective function. And the question is, where is the center of this circle and where is the center of that objective function contour circle? So it turns out that the centers of both those two circles are actually on the sort of the 45-degree line. And what I'm trying to show here is a special case when there is only 2 treatment sessions, just for illustration. So there's only 2 doses, D1 and D2. This is my 45-degree line. This is my feasible region circle. D1 and D2 are 2 doses in 2 sessions that have to be non-negative. So in this quadrant, this shaded gray region is the feasible region of the problem. The center of that circle is here. Okay, and the centers of those contour circles for the objective, which I'm also showing here as circles that are dotted or dash dotted, I think, right? Those centers, those are concentric circles with center here on this, the 45-degree line. And basically, the result is saying that if you look at what exactly the centers are, it turns out that the centers are negative alpha over 2s beta, comma, negative alpha over 2s beta. And the center here is alpha 0 over 2 beta 0 negative, and again, negative alpha 0 over 2 beta 0. So the proposition basically says that if the center of this circle is away from the origin as compared to farther away from the origin as compared to the center of this circle, then an equal dosage solution will be optimal. In other words, D1 and D2 will actually be equal. And what I'm trying to show with this star here is that that is where the optimal solution actually occurs. And the idea there is that, your circle center is here and you want to draw larger and larger circles corresponding to larger and larger value level sets. And basically the largest circle you can draw is the one that looks like this, and it just barely touches the feasible region circle at this 45-degree line here. So the equal dosage is actually optimal. The other part of that proposition is that the situation is actually flipped. Now this is the shaded feasible region, and its center is shown over here. And that center is actually farther away from the origin than this particular center of the concentric circles for the contours. And in that case, a single dosage solution is actually optimal. And you can see that the largest circle you can actually fit is where this circle intersects the feasible region, the gray shaded area. And that happens here where D2 is positive and D1 is 0, or here where D1 is positive and D2 is 0. Okay, so that's sort of further intuition in terms of what is going on in that problem. So let's actually go back to the problem that we wanted to solve. What we want to do now is we want to use this insight to actually figure out an optimal solution to the problem opfract 1, where of course n is no longer fixed, right? N is no longer fixed. So let's look at that quickly and see what is going on over there. And the way it looks is like this. What I have here is the first situation where alpha 0 or beta 0 is actually less than 1 over s alpha over beta. And as we know, in that case, just a single dosage solution is optimal. So just one treatment session. So I don't even have to worry about that case. But when alpha 0 or beta 0 is at least as large as this, then we know that an equal dosage solution with that d star n as the dose per session from that formula that I had derived by solving that quadratic equation is actually optimal. So I take that and I substitute that in the objective function. So remember that now I want to optimize n, and I have a formula for this dose per session. So what I'm doing now is trying to, n is the decision variable integer, at least 1, okay, and look at f star n, but f star n is the objective value that I obtained by substituting this dose, right, into the objective. And I did that over here. And I expanded that out a little bit more over here. So this d star n, as I said here, was obtained from equation 6 above. Okay, so I got this is square of that, and this is my expression for tau n. So this is the form of that f star function now, and I want to maximize that as a function of n, and n has to be integer. So it turns out that this function as a function of n now is actually concave, and it actually eventually decreases. And what that means is that you can see that this term, right, has an n here and a square root n here. This term has an n here, square root n here, but there is a square here, and this has an n minus 1 here. So eventually decreases, meaning this negative term in n, right, eventually overwhelms these positive terms in n, if you will, and the other terms in n that show up over here. Okay, so that's the idea. So it eventually decreases, meaning it is concave, but it cannot simply keep on increasing forever. And it is actually maximized at this value. Maximized at this value, meaning that you can simply, now that it is concave, you can simply take the derivative and equate it to 0 and figure out that it is maximized at this particular value of n star. And you'll see that there is some additional notation here, such as eta and r, excuse me, and that is simply r is equal to 1 over 2s rho, and eta is log 2 over t double. So that's basically the n star that maximizes this quantity. And of course, there are some subtle details here that I'm ignoring for the moment, but if you look at the tutorial paper, you will see that, okay, I had, n has to be integer, so I can, now that I know that this is the maximizer, I can take the floor and the ceiling of this and figure out which one of those two is better. And in fact, I had a constraint that says that n, the optimal n, has to be less than or equal to n max. So I can also incorporate that in my final optimal solution. But that's the idea. And this is how you can actually solve that problem exactly when there is a single normal tissue in your problem and a single modality, of course. Okay, so I'm going to continue on now. Okay, now let's look at how we can use the insights we have obtained so far to actually exactly solve the problem with multiple normal tissues. And in applications, in most cases, you would actually have this situation where you do have multiple normal tissues. So what we're going to do now is to first look at equal dosage solutions and single dosage solutions. Okay, and we're going to actually use the insight we actually obtained from the single normal tissue case. So here is the first point. The point is that we can actually figure out the best equal dosage solution to our optimal fractionation problem when n is fixed. And the way we can do that is as follows. So we know that at least one normal tissue constraint must be active. Okay, so what we do is we look at if the mth normal tissue constraint were active, then what would an equal dosage solution look like? And I explained how to obtain equal dosage solution by simply solving a quadratic equation earlier. And this is what is done here. So if that mth normal tissue constraint was active, then this is going to be an equal dosage solution, simply solution of that quadratic equation. So we do that for each normal tissue. And then the largest dose that you can actually give, right? Remember that the larger the dose, the better in terms of the objective function, is going to be the dose that is the smallest among all these doses for all normal tissues, right? So the smallest over these doses. And the reason it is the smallest over these doses is because if the dose is bigger than this number, then it is going to violate one of the, or that particular corresponding normal tissue constraint. And that's why this is sort of the bottleneck dose, if you will. And I'm going to denote that by C star of n. So this is the best equal dosage solution to that particular problem. And you can apply the same idea to figure out the best single dosage solution. So this is what I did for, let's say the mth normal tissue I figured out by solving that quadratic equation, single dosage solution. And then gamma 0 is the smallest among these because any larger would actually violate one of the constraints for one of the normal tissue. Okay, and then we can actually have sort of a counterpart of proposition 1, which is this proposition 2, which basically says that if the tumor alpha 0 over beta 0 is bigger than the largest of these ratios, if you will, then an equal dosage is actually optimal. Because this formula here simply tells us the best equal dosage solution. And this formula simply tells us the best single dosage solution. But we do not know when is best equal dosage in fact optimal, or in other words, when is equal dosage optimal. And this actually gives us sufficient condition for that, which says that the tumor alpha over beta ratio has to be bigger than this alpha over beta ratio. And of course, this is the sparing factor that is scaling that quantity. Then setting all these doses to this C star of n is actually optimal. On the other hand, if this is actually smaller than the smallest among all these ratios, then a single dosage solution is optimal, meaning set all the doses to 0 except 1, and that one should be set to be equal to gamma 0. That is an optimal solution in that particular case. Now, this actually does have some interesting clinical implications. Typically, in the clinical literature, people believe that for cancers such as head and neck, the tumor alpha or beta ratio is actually larger than the alpha or beta ratios, are actually quite a bit larger than the alpha over beta ratios for the normal tissue in that case. So typically for something like that, right, like head and neck cancer, this type of an equal dosage solution would be optimal when the number of treatment sessions n is fixed, and I want to solve that optimal fractionation problem. On the other hand, people believe that for cancer such as prostate, the alpha 0 over beta 0, so alpha over beta ratio for that cancer is typically smaller than those for all those normal tissues in that particular case. And then in that case, a single dosage solution would be optimal in that optimal fractionation problem. So what this actually means in terms of a geometric insight is as follows. So remember that we had that two variable problem in terms of x and y that was equivalent to our optimal fractionation problem when n was fixed. And I had shown you this sort of horn-shaped feasible region earlier. But in that earlier picture, I only had a single normal tissue. So I only had a single linear constraint there on x and y. But now I have multiple normal tissues. So I have all these constraints, each line corresponding to a particular normal tissue. And that's what I'm showing here. Normal tissue constraint, slope magnitude is this 1 over s alpha or beta, but this is the steepest among them. So this is the maximum among those. And if you go back all the way here, this is the flattest among them. So that's the slope magnitude. And that's why I'm calling this the minimum among all those. But those are the slope magnitudes for all these different lines. Okay, and as before, the objective function line has this magnitude, slope magnitude alpha 0 or beta 0. And again, in this picture, I'm showing sort of the same idea here, that if this was actually flatter than the flattest, right, then the optimal solution would appear here. Whereas this was actually steeper than the steepest, right, then the optimal solution would appear here. And remember, this is an equal dosage optimal solution, whereas this one is a single dosage optimal solution. So this is sort of the geometric insight, if you will, or pictorial insight behind that proposition that I showed you on the earlier page. Now, continuing on, one point that I do want to make is that proposition 2 does not address this case, right, where the tumor alpha over beta ratio is in between these two quantities, because it addresses the case where that alpha over beta ratio is this or larger. And it also addresses the case when this alpha over beta ratio is this or smaller, right? And that's respectively the equal dosage and the single dosage situation. But it does not address the case as to what will happen when this is in between. Okay, so I want to quickly show you a counter example, an example, I should say here. The parameter values themselves here are not important, but let's say if you use these parameter values and you plug those into that optimal fractionation problem with n fixed. So I dropped the tau n term because that's just a constant, so it doesn't matter for the sake of this discussion. Then you would get this convex objective function, quadratic, but it is being maximized. And I have d1, d2 here, right? And they are again linear quadratic, and these are the constants upper bounds. Okay, so this is the problem. And it turns out that if you did a quick calculation, so compute the minimum, right, as we have in the previous slide, it turns out it's 2.8 roughly. It turns out that with these numbers, the alpha over beta for the tumor is 5, and the maximum of those ratios is actually 6. So in this particular situation, this 5 is strictly in between 2.8 and 6. Okay, so this is the situation that is not addressed by proposition 1 or by proposition 2. Okay, in this case, it turns out that this problem has exactly two optimal solutions. In one of them, d1 star is 13.45, d2 star is 1.05, and the other one is sort of the swapped version of this, where d1 star is 1.05 and d2 star is 13.45. Okay, the important point here is that these are the only two optimal solutions to this problem. And in particular, this problem does not have any optimal solutions that are equal dosage or single dosage, right? Because you can see that, of course, this is not an equal dosage solution. There are two different doses in two different sessions. And clearly, there are not single dosage solutions because there are two doses that are being given that are positive, okay? So this particular situation is actually not handled by proposition 2, okay? So now how do we actually, so in that sense, right, how do we actually solve that problem with multiple normal tissues exactly? Remember that this situation did not occur and would never occur when you only have a single normal tissue, because the only thing is whether alpha or beta is for the tumor is bigger than the normal tissue, alpha or beta, or smaller, right? this in-between situation does not occur in that case, but it does occur in principle in the multiple normal tissue case. So then what do we do? So the interesting observation that is now known in the literature is that not only that you can use that two variable problem that I had shown earlier, but in fact, you can actually sort of convert it to, in some sense, an equivalent two variable linear program. So that's the important part here. So I'm sort of writing this as a lemma. So x star n and y star n is actually optimal to that two variable problem that I showed you a while ago now, right? At sort of the beginning of this tutorial. Okay, it's optimal to this problem if and only if it is actually optimal to this other problem. So this problem is also a two variable problem. But the constraint that we had before, which had all those square roots and so on in that constraint, now has been thrown out and has been replaced with a constraint that is actually linear in x and y. And this one is also actually linear in x and y. Okay, so that's why this is a two variable linear program. And this is a very powerful result because it says that the problem that was originally a non-convex QCQP, which in general are difficult problems to solve, right? This lemma shows that in fact that is equivalent to, right, or can be solved by instead solving a simple two variable linear program. In some sense, the simplest optimization problem that is out there, just two variables linear program. And the intuition behind this lemma is as follows. So please recall from the previous pages that I had shown you the feasible region for that problem in the XY sort of space, where I had this horn-shaped gray shaded feasible region, and all these lines were the normal tissue constraints, linear constraints, right? But we were talking about the fact that the idea is to push my linear objective that I'm not showing here in this picture, but to push that linear objective as much as possible that way, as much as possible outward, right? So we knew in that problem that the optimal solution only occurs on this sort of boundary, if you will, of that feasible region. And in that sense, this curved part of that feasible region is not really that important, right? That's the intuition you get from this picture. And therefore, instead of looking at this curved part, and in particular this curve, right, that's what makes that original problem non-convex, we can in fact look at this cone-shaped region. So instead of the horn-shaped region, we can look at the cone-shaped region. And that is what is being done here. In particular, those inequality constraints which said that x had to be in between square root ny and square root y are being replaced by this basically linear. So these two lines, which basically simply say that your y has to be bigger than c star nx and y has to be smaller than gamma 0x. And that's these two lines. Now, how were these two lines obtained? They were obtained by making the following observation. We know that this corner here is a single dosage solution. In fact, an optimal single dosage solution, if you will. And this one is an optimal equal dosage solution. And we know that that solution has this as the dose C star n, I discussed that earlier, per session. And this solution has gamma 0 as the dose in the single session, right? Therefore, we know essentially the coordinates of this basically. And in other words, we know the equation of this line that connects this point to this origin. And we also know the equation of that line that connects this point to the origin. And in particular, that equation is actually y equal to c star x, and this y is equal to gamma 0x, okay? And that's why I was able to replace those constraints, inequality constraints, with these linear constraints. And that is why that problem 2Rn is in fact equivalent to this linear program. And this is actually sort of what closes the book on that optimal fractionation problem with multiple normal tissues, meaning that just solve this two variable linear program and it will give you an x star y star solution, right? And that solution will be somewhere on this boundary here, right? If it is here, it's going to be a single dosage solution. If it is here, it's going to be an equal dosage solution. We already know the dose formulas for those. But if it is anywhere over here, use those equations that I developed at the very beginning, right, of this tutorial to actually figure out what the corresponding dosing plan should be. And that actually resolves all possible cases. So this is in some sense more powerful than proposition 2, meaning that it doesn't work only when, right, the alpha 0 or beta 0 is ordered in a particular way with respect to the alpha or beta ratios for the normal tissues, but this works no matter how they're ordered. So it handles all cases simultaneously. And this is what this leads to an algorithm for the exact solution of the optimal fractionation problem. And I don't think I need to go through the details of the algorithm. You can look at it here later, or you can look at it in the tutorial paper where I've included much more detailed discussions of this algorithm. But the idea here is basically that you can actually calculate all the quantities. You can calculate gamma 0, you can calculate Cn star when needed, right, for each n, and just solve that 2-variable linear program to obtain that pair x star y star that I just discussed a few minutes ago, right? Calculate the corresponding objective function value. This is the objective function value, and basically try doing this, right, for different values of n, and just maintain the largest possible value that you get, right? And that's going to be your optimal n, and you also have the corresponding dosing plan, okay, from the equations that I described at the beginning of this tutorial. So that is the procedure for exact solution of that optimal fractionation problem under multiple normal tissues with a single modality. Now we have seen thus far that the optimal fractionation problem with multiple normal tissues and single modality can be solved exactly. However, there is a limitation of the formulation of that problem itself. And the limitation is that the parameters rho m for the organs at risk or normal tissues are actually not known, and they're very difficult to estimate. And the uncertainty in these parameters is often discussed in the clinical literature. So one way to handle this uncertainty is through robust optimization. And in this part of the tutorial, I'm going to give you a very brief idea about how that can be done. So again, the theme here is that a robust counterpart of the fractionation problem can be solved exactly. In the interest of time, I will not have the opportunity to go through the details. So I encourage you to please look at the tutorial paper for those details. But here is the main idea. So one approach to handle uncertainty in the rho m parameters for the normal tissue is to change the formulation of that problem as follows. So again, let's look at the case where n is fixed. The objective function, I did not change it. I left it as it was. But I look at the constraint, and I'm saying now that there is interval uncertainty in this parameter rho m. So in particular, in the clinical literature, it typically is sort of possible, at least I think, to find intervals for these parameters rather than their actual exact values. So therefore, we are now saying that given that uncertainty, we want this constraint to be satisfied for all values of that parameter in that interval. And the interval is simply from some lower bound value rho min to some upper bound value rho max. And of course, this is for each organ at risk. So now this is the problem that we want to look at. And of course, the decision variable is still the non-negative dose vector. So let's look at this constraint. By the way, one point I wanted to make is that uncertainty in alpha 0, beta 0 parameters in this robust framework is actually easy to handle because they simply are appearing in the objective. So in a worst case analysis, you simply look at their smallest values because you're trying to maximize the objective function here. So that's why I'm not going to focus on the uncertainty in the alpha 0 and beta 0, the tumor parameters, but it is more interesting to look at the uncertainty in the normal tissue parameters rho m, partly because the rho m parameter actually appears on both sides of this constraint. Okay, so you cannot simply say that the bottleneck value, meaning that the value at which if I make sure that this constraint is satisfied, then it will be satisfied for all values of rho m in that interval. The bottleneck value is not evident or not obviously available because the rho m parameter appears on both sides of this equation. So for that reason, what I did was that I moved all the rho m terms to the left-hand side. So you can see that the rho m is here now. I collected this rho m term and I moved it to the left-hand side. And now right-hand side does not have any rho m parameters. Okay, so if I look at this constraint now, and then I'm going to say that, okay, I want this constraint to be satisfied for all parameter values of rho m, right, in that interval. So now you can see that if you are looking at this, then if this term here, the expression here, if that is positive, right, versus if that is negative, right, is going to actually determine the bottleneck value of rho m. Okay. In particular, if this dose squared sum term is actually bigger than this divided by this sm squared, that means this quantity is positive, right? Then that will be feasible if and only if it is feasible with this value rho m max. That's the idea, right? Because that is basically going to give me the largest value of this left-hand side, because this quantity is actually positive. So if I make sure that this constraint is satisfied, right, with this rho m max value here, then it will actually be satisfied for all values of rho m. And that is the case for doses whose sum of squares is actually bigger than this. On the other hand, if you have doses where the sum of squares is actually smaller than this, then this quantity here is actually going to be negative, and therefore the bottleneck value is rho m min, which is the left endpoint of this interval. So this is the main observation, and it turns out that using this observation, you can actually sort of reformulate this problem, right, into a finite set of sub-problems. Okay, so I'm not going to be able to go over the details of that, but it turns out that you can actually formulate that problem or reformulate that problem equivalently as a finite set of sub-problems. And the form of each of those sub-problems is actually quite similar to the problem that we have seen earlier, the optimal fractionation problem. You can further actually look at further subcases for each subproblem, and it turns out that you can actually solve those exactly via a simple procedure. So the details behind this are actually included in the tutorial. Okay, so I'm going to move on to another way to look at this uncertainty, and that has to do with inverse fractionation. And the idea in inverse fractionation is as follows. So again, let's fix n, and a question that is debated in the clinical literature roughly takes the following form. What values of the parameters, so the tumor parameters alpha 0, beta 0, as well as the normal tissue parameters rho m, would actually make a given dosing plan optimal to the optimal fractionation problem? So in this case, this dosing plan might be something that they are contemplating that they want to use, or this might be used commonly in practice, right? Or they may want to use this in a clinical trial. So this is a given dosing plan, and we want to actually figure out what values of the parameters will in fact make it optimal. And this is the reason that this is called an inverse fractionation problem. This problem falls within the general area of inverse optimization, where the idea is to infer the values of model parameters based on given values of decision variables. Okay. And the way we can actually look at this problem is again to go back to our variable transformation. X star is the sum of doses. These doses are given now, and Y star is the sum of squares of those doses. And again, utilize the equivalence between the optimal fractionation problem for a fixed n and the two variable problem for that fixed n. And it turns out that a closed form formula, and this is important, a closed form formula for all parameters that can make X star and Y star, like this X star and this Y star optimal, can actually be derived. The procedure itself is actually quite straightforward and in some sense elegant, although there is various cases that one has to consider. The explanation for that turns out to be a little bit tedious, but the procedure itself is actually simple in terms of the kinds of calculations that are needed. So this is a very interesting situation where typically in inverse optimization, it is not possible to figure out a closed form for all parameter values that make a certain decision variable optimal. But it turns out that you can again exploit the structure here and figure that out. So in the interest of time, I'm not going to be able to go over that. I do have slides for that here, but I'm going to skip over those slides. If you are interested in seeing how that can be done, please take a look at the tutorial paper itself, which explains in detail how to do that. Okay, so with that, I am for now done with my discussion of optimal fractionation with a single modality. And to quickly recap, I was able to show that the problem can be solved exactly for multiple normal tissues with a single modality. And I was also able to show how to solve the problem exactly, in particular in the robust case and the inverse case. Okay. Now let us look at the optimal fractionation problem with two modalities. The first modality is photons, which is the most commonly used conventional modality. And let us think about modality 2 as protons, which is an often discussed alternative modality in the clinical literature. Now, as I mentioned before, at the beginning of this tutorial, typically there is no clinically dominant, like universally dominant modality, and perhaps it is not clear which modality should be used for a particular cancer type, at least in some cases. And there have been literature in studies in the clinical literature, which even consider combination of two modalities, photons and protons in particular. So here is a fractionation formulation for a problem with two modalities. So I'm not going to say too much more about this other than the fact that there is N1 and N2 are the number of treatment sessions with the two modalities. I'm going to assume that the dose per session is constant at D1, which is a decision variable here for the first modality, and the dose per session is D2, which is a decision variable here again for the second modality. This objective is basically the same as before. It just adds the effect of two modalities together. And because the total number of sessions is now N1 plus N2, it uses the proliferation number or parameter for that. Okay. On the left-hand side here, again, it's the biological effect of the two modalities combined. You'll see here that the two modalities have their own alpha and beta parameters, superscripted by I for the two modalities I equal to 1 and 2. Similarly, their own sparing factors here. And again, this biological effect is less than or equal to what this particular normal tissue is known to tolerate. One important idea here is that on the right-hand side, I have used the parameters for the first modality because that's the conventional modality. And therefore, it shows up here as what is known to be tolerated. In particular, this is the biological effect of using a dose delta M via the first modality for TM sessions. And then doses have to be non-negative, and Nmax now is a bound on N1 plus N2, and N1 and N2 are integers here. Note that I am allowing N1 to be 0 or N2 to be 0, for instance, because I'm not assuming that both modalities are actually used. So in particular, if N2 turns out to be 0, optimally speaking, in this formulation or in the solution to this formulation, then that means that modality 2 is not used. Okay. So what I'm going to do as before is that I'm going to focus on the case where N1 and N2 are fixed. And again, once I can solve this problem with N1 and N2 as fixed, then I can actually vary the values of N1 and N2. It's just two integer variables. Sum is less than or equal to Nmax. So there's not that many values. And then figure out which one of the combinations actually gives me the best objective value. So in the interest of time, I'm not going to say too much about this problem, but let me just quickly give you some main ideas. So let's first look at the single normal tissue case and look at the analysis quickly. And then, it can be extended to the multiple normal tissue case as well. So now that since there is only one modality, and by the way, N1 and N2 are fixed, the problem can be written simply as this. I've dropped the subscript M from here because there is only single normal tissue in this particular case and two modalities. Okay, there is three possibilities. D1 could be positive, meaning I am using some positive dose with the first modality, D2 0, D1 0, D2 positive, meaning I am using some positive dose with the second modality and nothing from the first modality, or they both could be positive. So when D1 is positive, D2 is 0, I can set DT to 0 here and simply solve a quadratic equation. Note that this constraint has to be active at optimality, so I can get a D1 value. Similarly, for the second case, I can get a D2 value by again setting D1 to 0, and this constraint has to be active. But the third case is more interesting, D1, D2 both positive. So for that case, let's actually move on to this third case And here I'm going to use Lagrange multipliers lambda, mu1, mu2 corresponding to the inequality constraint, and then the dose non-negativity constraints, mu1 and mu2. Those are the Lagrange multipliers for that. I can write the KKT conditions. So these are the KKT conditions. Also, again, the constraint has to be active. So I've set this to be equal to B. And then the fact that both these doses are 0 from complementarity conditions, like these conditions, that means that mu1 and mu2 are 0. That can be used in this equation system 11 to actually figure out D1 and D2 in terms of lambda. Okay, and then you can take these D1 and D2 and plug that back in here. And when you do that, it turns out that you actually get a quartic equation in lambda. You can solve that quartic equation in lambda, and basically the solutions of that equation will give you candidate values of D1 and D2. So by doing this, you can basically figure out all points, D1, D2 points, or D1, D2 values that satisfy the KKT conditions. You also have the first two conditions, right? Where we had the quadratic solution for D1, quadratic equation solution for D2, and then simply compare and find the best among all these values. If you do have multiple normal tissues, then again, at least one normal tissue constraint must be active. So the first case is where exactly one constraint is active. Then you can apply the above method that I just described one by one to identify again all candidate solutions. And by one, I simply mean here that make one constraint active, apply the procedure, and make another different constraint active, apply the procedure, and so on to identify all candidate solutions. And then the other case is at least two constraints are active. When two constraints are active, you have only two variables, D1 and D2. So simply solve quadratic equations and you'll get candidate values of D1 and D2. Since there is M total constraints, because there is M normal tissues, you'll get M choose two pairs of quadratic equations to again identify all candidates. So in short, you can in the end compare all candidate solutions to actually find the best. So this is a way to actually exactly solve the two modality problem. And again, just like we discussed the robust counterpart of the single modality problem, you can also think about a robust counterpart of this two modality problem. Again, I'm not going to spend too much time on this, but the constraints in their form are the same as before. But now let's look at the case where these pairing factors have an interval uncertainty, and the alpha and beta parameters also have interval uncertainty. One of the reasons why I included this interval uncertainty for the pairing factors here is that especially for the alternative modality, so modality 2, which is protons, if you go back and look at the picture for its dose deposition profile, I discussed the fact that it has something called a Bragg peak, but the location of the Bragg peak is actually uncertain, and that can be captured in this model by using the pairing factor. Okay. So again, you can rewrite the inequality constraint as follows. Again, I'll not spend too much time on the details here, but the idea is that some of these parameters, their bottleneck values can be easily figured out. In particular, the ones that do not appear both on the left-hand side and right-hand side, their values can be easily figured out, and they're substituted here. But the main point is that for the conventional modality, the alpha and beta values, as you can see, appear on both sides of the equation. So their bottleneck values are a little bit harder to compute. And that's why we still have that here, okay, that this has to be satisfied, this constraint, for any value of alpha in that interval and any value of beta from that interval. And then just like the single modality case, the bottleneck value of alpha 1 in this case will be determined by whether or not this is positive. I mean, this is positive or negative. And similarly, the bottleneck value of beta will be determined by whether this is positive. This term is positive or negative. And it turns out that this can be used to actually sort of reformulate the problem into multiple subcases or multiple subproblems. So I'm going to skip over that detail. You can look at either the tutorial paper or the original paper that is cited in the tutorial paper to figure out what kind of subproblems one can actually solve or one has to solve. And they look like this. Basically, the idea is that their form is actually quite similar to the nominal problem, except that they have certain bound constraints. So again, those can be solved using an KKT approach similar to the one that I described for the nominal problem. So that's about what I wanted to say for this robust fractionation with two modalities. I want to conclude the tutorial by briefly outlining some variations that have been studied in the literature and some open problems or open questions for those of you who might be interested in working on those problems. So some variations first. One thing that I did not talk about is spatio-temporally integrated fractionation. So throughout this tutorial, the decision variables were doses, right, D. But in practice, of course, as I showed at the beginning of this tutorial, one has to actually figure out what intensity profile is actually going to be used to administer or deliver those doses. So you can actually write down formulations of the problem that I discussed, where the decision variable is not just dose, but instead it is actually the intensity profile of the radiation field. Okay, and work has been done for those types of problems as well, both in the optimal fractionation context as well as the robust counterpart. Also, there is work in the literature where these radiation intensities are actually computed adaptively based on observed tumor response. And in particular, there is literature about adapting these radiation intensities to the spatio-temporal evolution of hypoxia. Hypoxia here means a lack of oxygen inside the tumor. And in fact, lack of oxygen inside the tumor reduces radiosensitivity. So it is harder to kill that tumor or that part of the tumor. So there is literature about adapting radiation intensities to how the hypoxia is changing inside the tumor spatio-temporally. There is also literature that tries to learn tumor response parameters over the treatment course. The models that I discussed today were actually just static, robust models. So there was no dynamic decision making that was being done based on observations of response, and there was no dynamic learning involved in the models that I discussed today, but those types of models have also been studied in the literature. Also, the N, which is the number of sessions in all the models discussed today, was determined a priori in a static way, but there is literature about adaptively determining that treatment length or the number of sessions based on observations of tumor response. Some open problems. So inverse spatio-temporally integrated fractionation. So I mentioned that there is literature on spatio-temporally integrated fractionation, but there is no papers that talk about inverse versions of those, where an intensity profile is given, but based on that intensity profile, we want to figure out parameters, let's say for the normal tissue or the tumor. Also, sufficient and necessary conditions for optimality of single modality solutions are not known in the two modality case. So I mentioned the fact that okay, the one possibility is that only one modality is used. So let's say D1 is positive, D2 is 0. Another possibility is that only D2 is used. So D2 is positive, D1 is 0, but it is not known what are the sufficient or necessary conditions for that to happen. Also, inverse fractionation with two modalities, there is no paper that discusses that problem, where basically the dosing plan for two different modalities are given, and we want to actually figure out parameters, dose response parameters for the two modalities. So there is no paper that actually does that. Also, as I mentioned a few minutes ago, I made the assumption in this tutorial that the dose per session for each modality, so let's say D1 or D2 for the second modality, that is constant, but there is no paper that tries to actually generalize that to the situation where the doses are actually allowed to vary across those N1 sessions or those N2 sessions for the two modality problem. And this is unlike the single modality problem where I illustrated today, that problem can actually be solved exactly, but we do not know anything almost about that problem in the two modality context. And also, robust spatio-temporally integrated fractionation with two modalities has not been discussed in the literature. So that's another open problem that is of interest. Okay. So I think I'll conclude the tutorial at this point. I hope you have gotten some information about various problems that come up in this area. And if you're interested, please take a look at the tutorial paper to learn more. Thank you.